All right, guys. So in this video, we're going to talk about two concepts, electric flux and Gauss's law. And we'll start with electric flux because Gauss's law then incorporates electric flux into the calculation of electric field. So in the previous video, I showed you how in order to find electric field using the Coulomb's law, sometimes the calculation can be very tedious and difficult because if you have a continuous charge distribution, the calculation of electric field requires evaluation of that integral. Now, Gauss's law allows us to do the same type of calculation for an electric field, but instead of going into the direction of evaluating those difficult integrals, it allows us to get exactly the same answer using concept of electric flux and using the right symmetry of the problem to get the right answer in just several steps. The We're going to see that the calculations are much simpler, though only in certain cases that calculation can be simplified to only a few steps. But let's start with electric flux. In terms of then electric flux, you can see, right, it represents some electric fields, assuming that the source is really far away. So we're just looking at the field lines, right? Those are the field lines um, coming from that source, and they are parallel to one another. So you can see, right, those orange lines are the electric field lines. And then if we look at the electric field lines going through some area of interest, so let's say we have an area, let's say that, let's say square or rectangular area over there, and we have electric field lines going through that area. So then one of the things we can look at here is how many of those field lines going through that area of interest. So basically the electric field lines through the area of interest is then known as electric flux. And mathematically speaking, it's the product of the magnitude of the electric field and then the area of interest. So this phi here, capital Greek phi, is for electric flux, and the simplified equation for that is just E times A. That means the magnitude of the electric field, if we have that. So for example, if it's 20 newtons per coulomb, and let's say you have the area, I don't know, let's say 10 meters square, then the flux, if assuming that the flux is basically represents some electric field that is constant and uniform throughout the entire area, and it's moving such that the electric field is perpendicular to the surface of the area, then the calculation is basically as simple as then electric field magnitude times the area, which means that in this case, electric flux is equals to 20 Newton per coulomb, then times the 10 meters square for the area. So we just get, let's say, 200 newtons meter square per coulomb. Those are the units for the electric flux. So that means electric flux just represents the field lines going through that area A. And for this particular configuration, the flux calculation is basically as simple as electric field magnitude times the area. All right. So we're going to see that there's a little more general equation for the electric flux because there are, can be instances where the electric field is not uniform, or instances where electric field is not perpendicular to the surface. Then, we have to add more, let's say, terms to represent those extra parameters. So for example, if we have, let's say, a case where the surface is a little bit tilted, that means imagine right now we have this surface A over here, and then we're, let's say, changing the orientation. That means we're moving that a little bit, right? We're tilting it by some angle theta. So if we do that, then you can see, right? So from the previous slide, we're changing them at this angle theta. Then not all the field lines going through the area A anymore. Some of them are not going through the area A. For example, if I tilt it like this, now you can see, right, the bottom or electric field lines are no longer going through that area A. And in a way, we are decreasing the electric flux. But also, in order for us to calculate the electric flux for this new surface, we can see that there's a shift by this angle theta. So we need to incorporate that also into the equation. So then what we have here is the easiest way to kind of do that is to assume that there is a vector. That means, let's say, if you have things like this, if you have some kind of surface where the A represents the area of the surface, so basically this area of the surface. But then what we can do here is we can draw some kind of perpendicular to the surface vector. Let's call this vector A. So the magnitude of this vector A is then the area itself, area A. The direction of this vector A is, I'm going to put like n hat. What do I mean by n hat? So n hat is the unit vector perpendicular to the surface, perpendicular to the surface, which means it's always perpendicular to the surface, even if the surface is kind of moving around. So think like this. So right now, if I go back over there, so if I have this particular, configuration, then my electric field, which is perpendicular to the surface, will be in the same direction as this vector A, which then also will be perpendicular to the surface. So basically something like this. So this will be my vector A, which is also perpendicular to the surface. All right. But right now, when I tilt my surface a little bit, see the vector A, which always has to be true to the, to this, let's say, perpendicular to the vector parameter, right? That means like it's this vector A right there. So now I can see that there is a little bit of angle theta, right, with respect to the vector A and electric field. Electric field was pointing in the same direction before and after here. But then because I tilted my surface, vector A shifted by exactly this angle theta that I changed the surface. That means what I can do here is this. I can say that what I have here is my flux is then magnitude of electric field times magnitude of A, then times cosine of theta. And cosine of theta represents the fact that this is the angle that is shifted. And instead of, obviously we cannot use theta, right? Because theta, has units of radians. It's not something that we can use in the calculation. We usually use either sine of theta or cosine of theta or tangent of theta. And for this particular, configuration, it's cosine of theta. Because in a way, our goal here is to see the field lines going through the area A. And if I look at this electric field and break it down into two components, so this is a component that is, perpendicular to the area, and then there's another component that is parallel to the area. That's this, component of this electric field. I can see that this component that is parallel to the area is not going through the area at all. So I can just completely ignore that. But the component that going through the area is then adjacent to this angle theta. So that's why I'm using this cosine. That means basically you can say that effective electric field, which is then perpendicular to the surface, right, is equals to E cosine theta. Okay. So that's why it becomes, instead of E times A, becomes EA cosine theta. All right. In this particular case, if I go back and use the same quantities that I had, which is 20 Newton per Coulomb, then times 10 meters square. Then now if I do cosine of any angle, for example, I don't know, cosine of, let's say 30 degrees, see, I'm gonna get a smaller flux, okay, smaller flux. That means I actually decreased my electric flux by changing the orientation of the surface, which in a way shows by, let's say, identifying that now less electric field lines going through the area. So it makes sense that flux is less. Flux itself is a scalar quantity. Okay. That means it doesn't really have any direction. So it has a maximum value, it has a minimum value, let's say in terms of zero. It also can have a negative value, right? We're going to see. But the idea here is that electric flux as a quantity is proportional to the number of electric field lines penetrating some surface. If there's no electric field lines penetrating the surface, then you can say that electric flux is zero. Okay. So you can write the flux is zero when the surface is parallel to the field. And let's say here I can show you that in terms of thing like this. If this is my area right now, All right, so let's say if this is my area, and let's say now the electric fields are like this, right? Then what I can say here is I can say that my electric flux is zero. Why is the electric flux zero? Because if I'm doing E a cosine of theta, the theta is between vector A and electric field, and you can see right they are perpendicular to one another. That means angle theta here is 90 degrees. So if I put cosine of 90, I'm going to get zero. And also you can see that there are no field lines going through that area. So I'm talking about this picture over here. All right, that means, what we did, we went from maximum flux to some intermediate flux and then to zero flux. That means flux changes depending on number of field lines going through that area. All right, so we're gonna now find more general equation for the flux, because in a way, one of the things we have here is you can have any type of, a surface with, let's say, also like some general, area. So electric flux, you can see, right? So let's say you have a surface like this, and let's say there's electric field going through that surface. So I can say, all right, so here's my electric field going through that surface. And then what I can say is that A is the total area of my surface. But then I'm going to carve out a small piece, and I'm going to look at, all right, so electric field going through that, small element area, so that it has a size of delta A. Okay, so it has a size of delta A. Again, that black arrow represents the, area vector. And then the theta I represents the angle between an electric field and that, element area vector. So then again, then the flux using that equation is electric field through that surface of interest times then the area of that surface of interest, which has a height of delta A, then times cosine of theta I. Now, if you remember your mechanics class, over there we learned that if you have two vectors, and you can say, right, we have two vectors, vector E and vector delta A. And then this flux as a quantity is technically product of those two vectors. In this case, I'm like delta A. So we actually, multiplying two vectors together. And if you remember, if you're doing the product of two vectors, and the answer here is a scalar quantity, then that product represents a dot product. That means you are basically doing a dot product, and that's what we have. The flux is a dot product between two vectors because our answer is a scalar quantity that doesn't have a direction, just have a, as a, some kind of number and a unit associated with that. So another thing that we used to calculate using the dot product was work done. Remember work done, the energy? So it was F dot dA, F dot ds or F dot dr, right? Which is the force and displacement. So the dot product of force and displacement was the work done. So now we have dot product between electric field and then the area. And another thing, if you hopefully remember about dot product, it was that if you're doing that dot product of two vectors, A dot B, this was equals to A times B times cosine of theta. That means product of their magnitude times cosine of angle between them. And that's why we have, you know, um, let's say we had this equation, right? So we had this equation where it's EA cosine theta because it is, after all, a dot product between two vectors. All right. So the general equation then for the electric flux, because let's say if your electric field, maybe not uniform, throughout the surface, then if you're doing this flux, you're gonna end up then looking at this small area like this, and then carve another small area and another small area and another small area, another small area, and then just sum them up. And then at the limit where the delta A approaches zero, this sum end up being an integral. That means the flux is then the surface integral of E dot dA. All right. So if you, let's say now looking at this, integral, it's a surface integral and you're scared, don't worry about it. It's really not a scary surface integral because our goal here is we're going to see, right, when you're calculating the flux, we're going to want to make this calculation as simple as possible. For example, it's E dot dA. That means in a way, what I have here is If I know the magnitude of A and let's say dA, this becomes just then E cosine theta dA. And if I have then the theta, for example, if theta here is 90 degrees, then cosine of theta is 1. So then this becomes just EDA. And if, for example, I find the correct symmetry where the electric field has the same magnitude everywhere around my surface, then it becomes just, I can remove that. So it becomes E, an integral of dA, which is nothing but E times A. So that's why going back all the way to this surface, okay, I can say that this is my electric flux, which is an integral, surface integral of E dot dA becomes an integral of E dA or E cosine theta dA. But you can see, right? Remember, electric field is constant and theta here is 0 degrees. Again, theta is 0 degrees because I'm looking at the theta that is between vector A and electric field. And both of those vectors pointing in the same direction, theta is 0 degree. So then this becomes just integral EdA because cosine of 0 is 1. And then because electric field is uniform, I take it out, then I'm doing integral of dA. Then surface integral of dA is nothing but E times A. That's why electric flux for this is just E times A. That's why I said in the beginning it's a simplified equation because technically we should start with this and then we can see that it's simplified to E times A. All right, so here the cosine theta is not 1, so we technically include that. But if theta doesn't change, your answer again becomes EA cosine theta. All right, so coming back over here, so that's basically our general equation. That means general equation is an integral of E dot dA. Okay, this is an equation for the electric flux. Okay, so electric flux is a surface integral between electric field and dA. So again, dA represents that small element that we chose of this total area. But the idea here is that once you find the expression of just some small element, and then you generalize it and saying that this surface is then the collection of those small elements, and we're just summing them up, and that's why it becomes an integral. All right. So this is let's say a calculation or the equation for the electric flux. Now, one of the things we can do here is, let me show you a quick example. All right, so let's say we have let's say a cube like this. Okay, and let's say in this region there's electric field going like this. Okay. And then what we want to do here is we want to, let's say, find the electric flux for this surface. So what we can do then, for example, take this to be on the x-axis and y-axis, kind of like we draw a vectors like this. Okay. So, and we can see that, this is our coordinate system, y, x, and z. And I want to find what is then the flux for here. So what I can do here is I can see that there are, surface. Let me see, try to go back. Okay. So there's, let's say this surf. I don't know what does that. Okay, so let's say that surface over there where the electric field coming in, and let's say then this surface here where the electric field coming out. All right, and those are the two phases where the electric field coming in and coming out. Then what I can do here is I can draw this, let's say this vector A, which is then, or I can say like, dA, right? So this is for this, let's call this phase 1. This was phase 2. So then dA here will be in this direction, dA like this. So surface 1, surface 2. Then I have, let's say, this surface over here. So this one over here. I don't like that this guy does this, but you know. All right, so let's say this is then surface 3. So then here electric field will be, sorry, dA will be in this direction. Okay, the same thing is, right? So dA will be in this direction. So let's say call this, a surface 4. And then the 5 will be then dA in that direction. And then another one you can see at the bottom, dA in this direction. Now, one thing we can see here is if I'm calculating the electric flux, so this is flux for surface 1, plus flux for surface 2, plus flux for surface 3, plus dot, all the way flux for, I have, you know, uh, so 1, 2, 3, 4, 5, and 6 phases. So all the way to 6. And this is all just integral of surface integral for the surface 1, right? E dot dA1 plus surface integral for the surface 2, E dot dA2, okay, plus surface integral for the E dot dA3 plus dot. Same thing for all of them. All right, so important thing here to see is that if I am looking at surfaces, let's say 3, then 4, which is the top, and then the 5, which is, facing, YZ plane, and then the 6 over here, they all basically going to be 0. Why? Because when I'm writing the flux, let's say if looking at the closed integral, so E dot dA, let's say 3. So then what I will do here is that I will say then E dot dA as a dot product, remember? But this is basically EA cosine theta. But for the surface 3, I can see that electric field is some E I hat because it's pointing in an I hat direction. Electric field is in an I hat direction. But my dA here is equals to dA k hat, right? So that this dA3 here is in a k hat direction because it's pointing in a z direction. So if I'm doing here E dot, let's say dA3, I'm going to get 0 because electric field is perpendicular to dA3. And the dot product between two perpendicular vectors is always 0. That means this is 0, the 4, the 5, the 6, they're all 0. And the only surviving ones are just 1 and 2. For 1, it's going to be then E dA cosine of 0 because dA1 pointing in the same direction as I had, which I can also see that E dot dA1 is same as E dA dA1, right? Then I had that I had, which gives me 1. So then let's say put 0 degrees, then plus surface integral of E dA2, which is this one over there. And then here I'm going to get cosine of 180 degrees because electric field is in I hat direction, but dA2 is pointing in a negative I hat direction. So then it's a cosine of 180. Same electric field, same dA, add them together. This one is positive flux. This one is negative flux. I add them together, I'm going to get 0. That means the flux for this particular, let's say, object, right? This a rectangle or the square, right? Where the electric field coming from one side and exiting another side is going to be 0 because this surface 1 gives me a positive flux because the flux coming, the electric field coming out of the page. Then for the surface 2, where basically electric field going into the surface, into my surface, right? The dA2 is in a negative I hat direction, which then gives me negative flux. So that means whenever the electric field going into the surface, that's a negative flux. Whenever the electric field coming out of the surface, that's a positive flux. All right, so let's go back to the lecture notes. So then what I have here is, for example, if I'm looking at this particular surface, see electric field coming out, then I get a positive flux. Okay. All right. Now let's talk about Gauss's law. So the Gauss's law is an expression of the general relationship between the net electric flux, which is we talked about, through a closed surface and the charge enclosed by the surface. The closed surface is often called a Gaussian surface. That means one of the things one of the things that we have with the Gauss's law is that it represents how we can relate electric flux to the charges incorporated in this in the surface. Now, for example, Gauss's law takes the electric flux. We just saw that it has the information about electric field, right? So that's like this is E dot dA, and then it says that this can be used to find electric field, but then this quantity is also proportional, right? It's related to a charge within some kind of surface. Okay, so we call charge enclosed. That means, for example, if I have a charge, let's say it's a positive charge. Let's say if I have some positive charge, nothing like this. This positive charge, we know that it generates electric fields in all the space around it. So if I write down or draw the simplified electric field lines, it will be something like this, right? So this will be the electric field generated by this charge. So let's call this charge Q, positive Q. Now the idea here is then if I take this and kind of like surround this charge with some kind of surface, and this could be like imaginary surface. So that's why we call it a Gaussian surface. It's some kind of closed surface, and we can just assume that's kind of imaginary surface. Then one thing we can do here is we can then relate the electric field on the surface on the surface of this Gaussian surface, right? Um, to the charges inside that surface. That means we can say that there is an electric flux, right? There's electric flux because there's a charge inside. Okay, because if think like if I go and look at draw some kind of surface, can be something like this, can be something like that, can be something like this, right? If there is no charges inside, that means the electric flux for the surface is zero. Now, remember we just looked at an example, right? Where there's a some kind of a cube like that, and there's electric field coming from one side going to the other side. And what did we find for the total flux? We found it zero. Why? Because this electric field was not generated by some kind of charge inside that surface. It was some kind of external, somewhere really far away, and the flux for this surface was zero because there were no charges inside. So there was no charges inside. But if there are charges inside my surface, then I can relate that to the electric flux, and I can use that then to find the electric field at some point of interest. So that's kind of what the Gauss's law does. So it's an expression of the general relationship between net electric flux through a closed surface and the charges enclosed by the surface. All right. So um, let's look at an example here. Let's say there's a point charge Q. And let's say I want to find the electric field at some point P right here. Okay. Now, what I do here is we learned, right, that there's basically the equation for the electric field for the point charge. Okay. But I want to then sort of like relate in terms of how we can see how the flux is related to the charges inside. So let's say we have a positive point charge Q, and then we surround that point charge by imaginary sphere. We call it Gaussian sphere, right? Gaussian surface or Gaussian sphere. And then I say, all right, so since this is the point charge, right, it's going to have an electric field all over like this, right? So it's going to have electric field is going to be radially moving away from this. So then I take a small area from that sphere, right? Like let's say it can be anywhere. Like let's say I choose this one over here. It has a size dA, and I say, all right, so the flux is E dot dA. Okay. Again, so you can think of like let's say you can use a general equation, but the idea here is that I'm assuming that it's a small enough area where electric field is uniform and constant for that area, right? So then you just basically E dot dA. Now, N is the representative of the normal. That means normal to that surface. So En dA, right? I is just the I, let's say surface. So that becomes just E dA. Okay. That means this is basically the flux equation. So the net flux then will be E times A, where I'm saying that, for example, this is for that small, element surface. Then I have another one, and I have another one, and I have another one. If I'm adding them all together, this becomes basically, let's say, E to the surface 1 times delta A1 plus E to the surface 2 times delta A2. And when I factor out E, since E is the same for all of them, it just becomes some of those small elements of delta A, okay, which adding them all together gives you nothing but the total surface A. That means flux is E times A. Now, what is then, let's say, electric field due to a point charge at some point P? Now, the point P here is taken such that it has the same size as my imaginary surface. Okay, that means point P is same size or same distance away as that, this Gaussian surface. Now, what we know here is that electric field due to a point charge is kq over r squared. That's the equation for the electric field at that point P, that distance r from that point charge. What is the area of the sphere? Well, it's 4 pi r squared. Multiplying them together, r squared cancels with r squared. Then what we have is that 4 pi k electric constants times q. Okay, that means we have this. All right, now for a spherical surface, right, then the flux is equals to EA. Again, so same thing here, right? 4 pi KE times Q. Now, what we get here is that if I rearrange this, if you remember, KE, another way of writing KE was 1 over 4 pi epsilon naught. Remember, right? KE is 1 over 4 pi epsilon naught. But you can already see that in this equation, what we have is this flux is proportional to this term on the right side. Now, what is this? 4 pi is a constant, k is a constant, and the only thing there that has a physical meaning is the q. That means this shows that flux is proportional to q, everything else is a constant. Now, okay, so remember, ke is 1 over 4 pi epsilon naught. So then what we do a lot of times here, if I replace this, ke with that, so it becomes 4 pi, then times 4 pi, 1 over 4 pi epsilon naught, what's k, that's what k is, right, times q. 4 pi cancels out, and then what we end up with is this. That means flux is equals to q over epsilon naught, because that's the only thing survives. And that's what technically Gauss's law represents. That flux only depends on the charges enclosed in your area of interest. That means, for example, if you have a point charge like that, then you can find electric field that can be related to either this surface here or that surface over there or this surface here. It doesn't matter. It's actually independent of the type of surface you choose. Okay, you always can relate flux to the charges inside, as long as whatever surface you're choosing, there is a charge inside. So technically, this is, to be honest, is like a net charge, because if you have another charge which is negative, same magnitude, you can, if you add them together, you get actually zero. So the flux will be zero. But this is the equation for the Gauss law. It says the net flux through any closed surface surrounding a point charge, there's over there, point charge Q is Q over epsilon naught. Okay. And it is independent of the position of the charge within the surface. That means, in a way, once I have a charge, it doesn't matter what type of surface I have. Could be something like that, could be something like this, could be something like that, right? The flux is equals to the charge inside my surface divided by epsilon naught. Okay. Now, why is this, let's say, important? Well, because we also know that flux holds information about the electric field. That means then I can use the flux. If I know what flux is, and it's very easy, right? It's Q over epsilon naught. That means I can calculate flux. Then I can say flux is also equals to E dot dA. That means I have found a very easy way of calculating flux, which is Q enclosed over epsilon naught. then I can say that this is equal to then close the integral of E dot dA. So if I have the left side of the equation, then I can use that to find the right side of the equation, or find those together to get the electric field. Because remember, our idea here is to find the electric field in a simplest possible way without using that Coulomb's law, that all those tedious calculations. Okay, so let's assume that, for example, we have four charges: Q1, Q2, Q3, Q4 over here. And then we have different surfaces. So surface S, S prime, S double prime, and then we want to see what is the flux, for example. So if I'm looking at the flux for surface 1, well, flux for surface 1 will be closed integral, because it's a closed surface, of E dot dA, or E dot dA like this. Let's say, let me put like in terms of surface S. Well, this will be equals to Q1 over epsilon naught. And it's a non-zero flux. It's a non-zero flux. That means I can use this to calculate electric field for that. Okay. Yes, Q1 is negative. That means, I'm going to end up finding out that my flux is negative. For flux 1 is negative for that surface 1. How about if I do the same thing for, let's say, surface 2? Okay. So basically, this would have been negative Q over epsilon naught for the surface 1. For S prime, let's say, S prime. Well, S prime has Q2 and Q3. So this would have been a net Q over epsilon naught. But because Q2 and Q3 has, assuming same magnitude, opposite polarity, this would have been 0. That means my electric flux for that surface S prime would have been 0. And that's because the net charge is 0. Okay. Now, you can also think of it like this. So there's an electric field generated by the Q2, which goes out of the surface, gives you positive flux. But then there's also electric field due to Q3, which goes into the page. And then the flux, goes into the page, is negative. Flux goes out of the page is positive. That you add them all together, you're going to get 0. All right, so how about the surface S double prime? Well, if I'm doing S double prime, then I can say that if I'm looking at the dA, if I'm looking at the Q enclosed over epsilon naught, well, I'm going to get 0 because simply there are no charges inside. Okay, and then the same thing with Q4, right? Q4 is outside, and it doesn't contribute to any of the flux calculation for surface S, S prime, or S double prime. Because let's say what we have is that the electric field for this one goes in here and comes out over there, so it doesn't make any contribution. So negative flux, positive flux, so the flux contribution from Q4 is basically 0. So that's how we can use that to find then, information about the electric field. Okay, because what we have here, Gauss' law states that flux is the integral of E dot dA, but it's also Q enclosed over epsilon naught, or inside over epsilon naught. And that equation assumes that Q in is the net charge inside the surface, and the electric field is at any point on the surface. That means what I can do here is this. If I have a charge, Q, I want to find the electric field at this point P. What I do here is I create some kind of Gaussian surface, and then I find evaluate this integral for that surface and find the expression for electric field. And that is basically the electric field that I need from that charge at that point P. The idea is that we need to find the right symmetry. Otherwise, the calculation is not very simple. So that's why it's important to find the correct symmetry. And I'm going to talk about, let's say, when to use the correct symmetry for which configuration. All right, so the surface used is called the Gaussian surface. All right, so Gauss's law is valid for electric field of any system of charge or continuous distribution of charge. That means, if you're talking about just the point charge or system of charges, Coulomb's law is just as simple. When you talk about continuous distribution of charge, remember, Coulomb's law becomes very tedious and difficult. This is when the Gauss's law becomes more appropriate and a better way to go. Because, right, although Gauss's law can, in theory, be solved to find E for any charge configuration, in practice, it is limited to symmetric situation. So we have three symmetry that we can use: spherical, cylindrical, or plane symmetry. Those are the three, symmetries that we're going to be using, right, to find the electric field. Because if we have those symmetries, right, then electric field can be calculated using Gauss's law in like 2 or 3 steps without really doing very difficult integrations. Right. So remember, the Gaussian surface is a surface you choose. It does not have to coincide with the real surface. It's an imaginary surface. You're just using that to do that evaluation of that integral. Okay. So that's why a lot of times information about that surface basically end up dropping out. The only thing you want here is, you know, being able to show that flux is somehow related to the charge inside and use that to get the correct answer that we want. All right, so a few things. The Gaussian surface should satisfy one or more of these conditions. The value of the electric field can be argued from symmetry to be constant over the surface. That means we want this. Why? Because if the electric field is constant over the surface, it can come out of the integral. And the integral just becomes integral of just dA. If you cannot remove, the electric field from the integral, then it becomes no easier than the Coulomb's law. The dot product can be expressed as a simple algebraic produced EDA because of the electric field and the area vectors are parallel. Because we want to find the configurations where, that basically theta equals 0 degrees. So then cosine of theta is equals to 1. So just basically just EDA. That then the dot product is 0 because the electric field and the area vectors are perpendicular. That means, we can always say, just like that, I showed you that example with the surface, with the cube, right? So if electric field and the area vectors are perpendicular, then there is no flux. If there is no flux, that means that due to the fact that maybe there is no charges inside, or the net charge inside is 0. All right, so the field is 0 over the portion of the surface. That means, in order for us to apply Gauss's law, all of these conditions must be satisfied, and then the evaluation can become relatively straightforward. All right, so let me quickly show you in terms of what type of symmetries and what should we use in order to get the correct um, configuration. All right, so let me give you a table. So let's say this is the symmetry. And let's say again, so we have 3 symmetries that we have. So cylindrical, so cylindrical, um, let's say planar, and then spherical. And pretty much I'm going to show you in terms of how to use all of those. So that means, when to apply this type of, symmetry, let's see what type of system should we have. So for example, if you have an infinite rod, then we can technically have this cylindrical, that's a cylindrical surface. So let's say, thing like this. So like infinite rod. So something like this. So some kind of rod that kind of goes and extends all the way from positive infinity to negative infinity. And if I want to find some kind of like, electric field at some point P, I showed you in a previous video that, using Coulomb's law, right? I have to, have a small element, dx, dA, and things like that, and then use that to find electric field, which can be relatively tedious. But here, then what we're doing is we're going to then apply this Gaussian surface. And then the Gaussian surface that is appropriate for this type of, symmetry and system is coaxial cylinder. Coaxial cylinder. That means what I do here is this. So let's say I want to find electric field at that point P. Now, then I take and I assume that, let's say there's an imaginary coaxial cylinder around this, around this rod, such that, let's say here's that cylinder, right? Such that its size distance, right, from the center, this distance r, is exactly same size, same distance as the point P of interest. Right? That means this is what I want. That means this r is same as point P. So then if I do that, say for example, if this electric, this rod has a positive charge distribution such that electric field kind of goes like this, then what I can have here is that over that surface, let's say this curved surface, curved part, electric field all exactly same magnitude. And for this, circular surfaces, there is no electric field. That means what I can do here is I can look at in terms of the flux for this surface one, surface two, this curved part, and surface three. So then define flux plus one, plus two, plus three to get the negative net flux, and I can say this is equal to the Q enclosed over epsilon naught. Okay, so I'm going to show you an example how easy it is to do that. All right, so then I have a planar for which it is sort of like, let's say, infinite plane. So some kind of infinite plane. And what we use Gaussian, what we call pillbox. Okay. Now, what is that? So let's say you have some kind of infinite sheet like this. Then assume that it's extend all the way to infinity, right? So what we do here, we just use some kind of pillbox like this. So it goes like this and comes out of the other side. So that's, uh, electric field here kind of goes like this through that. I have the example here, that I can show, right? So, and then what we do here is then we can say the flux again. So we have the curved part and then this circular part, and we're looking at the electric field through those. Okay. So let me finish this table and I will show you an example of that. Then the spherical, which is generally a sphere or a spherical shell. Okay. And then for that, we use concentric, let's say, spheres. See that? That means this table allows you to see what type of symmetry, where type of system is applied, and what type of surface do we use. Okay. All right. So again, if we look at in terms of, let's say, the cylindrical, right? If you're looking at the cylindrical, let's go back then and look at an example for that. Okay. So here's an example. So you have an infinitely long rod of negligible radius, has a uniform charge density lambda. I want to calculate the electric field at the distance from the wire. So distance, let's say distance r from the wire, sorry. Again, so very similar example I did in the previous video. So the idea here is this: if you look at this, this rod from here, right? So let's say you're looking from here, you see this. That means the this is, let's say, rod toward you, right, out of the page. Then the electric field it generates is radially away from the charge, from this rod, because it's uniformly distributed, where lambda is the linear charge density. Remember, it's equals to total charge over the total length, right? And put like L is the total length generally. And this is then equals to then also, if you remember, right? So in terms of like, let's say, dq dl that we had before. Okay. So, but the idea is that this lambda is that charge per unit length. Okay, and it doesn't matter which size, which element you're choosing. I talked about that in the previous video. The idea here is this. See, if I want to find the electric field at this point P, for example, here's my point P. Then see, I surround that by a Gaussian, you know, a cylinder like that, right? So that means this green cylinder is an imaginary cylinder around this infinitely long rod. But I choose that cylinder such that when I'm looking at the size r, right, it is basically as same size as you know extends all the way to that point of interest, point P. So that's why when I calculate the electric field on the surface of that cylinder, I'm basically calculating electric field of that point of interest. Now, what I have here is then this. I am looking at the cylinder, and I can see that electric field, you can see, right, the electric field is generated by this rod such that it goes like that. Something like this and goes like this. So then I have three surfaces. Here's my surface one, here's my surface two, and then the curved part is my surface three. Okay. All right. So let me then get rid of those things so it's a little bit cleaner. And let's look at, for example, surface one. This is my surface one. See, for surface one, I want to calculate my flux, which is closed integral of E dot dA1. That means I have a vector dA for that surface one, and I do the dot product in the closed integral of that product. But I can see for my surface one, electric field is perpendicular to the dA vector. That means dot product between those two perpendicular vectors is going to give me 0, which means there is no flux for that surface one. Same thing I do for surface two. Close integral E dot dA2. And this is my dA2 for this face of that cylinder. Again, I can see that electric field and dA2 are perpendicular to one another for that face as well. So that also has 0 flux. Then finally, I'm looking at the face, the curved part, right? This one over here, where if I carve out some kind of area like this, then dA will be in the same direction than as electric field. That means I can say, all right, so flux 3, which is then closed integral of E dot dA3, finally is non-zero. Okay. Now, this, this surface integral can be simplified because it doesn't matter if I'm choosing this part or that part, right? So remember, so this is basically my cylinder, which is a distance r. See, everywhere it's same distance. That means along all my surface, electric field is uniform and constant. So this becomes E closed integral of just dA, and that's nothing but just E times A3, let's say. Okay. That means electric field times area 3. Area 3 is the area of that curved part of the cylinder. And according to Gauss's law, this is equals to Q in over epsilon naught. Okay. Now, I need then two things. What is the area of that curved part of the cylinder? And what is the Q in? Okay. Now, Q in, what I know here is this, right? So this is, if you remember, using this equation. So if I can say this is some, Q over L, that means I have a cylinder of this size L. See, this big Q is the total charge of the entire rod. But Q in is how many charges I have just in this length L of the rod where I have my cylinder, Gaussian cylinder. That means this, lambda then equals Q in over length L of the cylinder. That means Q in equals lambda times L. Then I can say this is equals to lambda times L over epsilon naught. So electric field times area 3 is equals to lambda L divided by epsilon naught. Now, what is area 3? So then area 3 is, if I rearrange this becomes electric field equals then lambda L over epsilon naught then area 3. Then I can say that electric field, remember, our goal is to find the expression for electric field at that point P. Then electric field is equals to lambda L divided by epsilon naught area 3, and area 3 is area of the cylinder, that curved part, which is 2 pi r times L. And then here you can see that all the information about L cancels out, and I don't need that, right? Because that's the size of my imaginary surface. That information, not part of the calculation for electric field, because I can choose, this size of a, imaginary surface. I'm going to get still same expression because the length is just length of my imaginary surface. It can never be part of the electric field actual calculation. That means electric field then ends up being lambda over 2 pi epsilon naught then times r. And that's the electric field, which you go back and look at how I derived this using the Coulomb's law, is exactly the same thing. And you can see, right, all I did is say that All right, so the flux through surface 1 and 2, 0. Flux through surface 3 is E times A, E times A3 equals Q inside over epsilon naught. All I needed to do is Q inside is lambda times L. Then equate those two and find the expression. I didn't need to do any difficult integrals. And that's the beauty of the Gauss's law. It allows you to get the equation for the electric or expression for the electric field in just simple 2-3 steps. All right, so let's look at then another example over here. So this is then for the spherical symmetry. Okay, so for the spherical symmetry, then what I have is this: an insulating solid sphere of radius A has a uniform volume charge density rho and carries a total charge, which is Q, total positive charge Q. Okay. Now, you can have two things. So important to understand that this is an insulating sphere, insulating solid sphere. Okay, so insulating solid sphere. Because you can also have a conducting solid sphere, where the conducting is generally, some kind of metal, material. So let me actually go back to here and show you that. So for example, let's give you two more examples quickly here. So I have planar that as I mentioned, right? I want to, show you in terms of how to work with the planar symmetry. And for this one, what we need here is some kind of, let's say, a surface like that. Remember, this is generally planar is two-dimensional, right? So where you have the charges kind of distributed, uniformly on this, plane. And this is just sort of like a sample of that, right? It kind of extends. So where A is the area of, whatever small piece of that total, infinitely, plane that we're considering. And remember then sigma represents surface charge density, where it's basically Q over A. Okay. Now, what I have here is then electric field then goes like this. Right? So electric field is like that, and also in opposite direction. Now, what we do, we choose some kind of pillbox, which is basically a cylinder that kind of penetrates the surface from here and comes out from the other side. Like that. Okay. And for this one, you can see, right, that then technically the electric field kind of like coming out of this surface over here, this face. So it has, again, three surfaces, right? Surface 1, surface 2, and surface 3 is that curved part. So if I'm finding the flux, for example, for the surface 1 is integral of E dot dA1. Well, electric field that coming out of this surface, right, is the same everywhere. Like that means over this surface is the same. So that means I can say it's E surface integral of dA1. So it becomes E times A1. Okay. Again, the idea here is to find the symmetry when you end up with this. Same thing we do for the surface 2, which is right here. We can say, right, electric field goes, parallel to this dA2, and this was like dA1. And then I can say that flux 2 is equals to closed integral of E dot dA2, which again, because electric field is constant around that, surface 2, becomes closed integral of just dA2 or just E times A2. That's flux 2. How about flux 3? Well, flux 3 is this part. So if I carve a small piece and do the dA3 like this, I can see that electric field in this direction is perpendicular to dA3. That means the flux of E dot dA3 going to give me 0 because no electric field lines going through that curved, region. But if I do then the flux net is equals to flux 1 plus flux 2 plus flux 3, I'm going to get flux 1 is E times A1 plus flux 2 E times A2 plus flux 3 0. So then what I get here is I get 2 times E times, and since A1 and A2 are the same, I get 2 times EA. All right, so that means the left side of the Gauss's law, where flux, which is in terms of E dot dA, this is the net. So then we got this in terms of then 2EA. The right side of the Gauss's law then is Q in over epsilon naught. Now, what is Q in? Well, Q in over that surface area A is, you remember, is equals to surface charge density. That means Q in is then sigma times A. I can write it like that. That means I can say that Q in is sigma times A then over epsilon naught. That means I have this 2EA equals sigma A over epsilon naught. And I can cancel the A from both sides. Then what I get here, electric field equals sigma over 2 epsilon naught. Like that. And that's a very interesting, result, because look at the electric field dependence. It's equals to sigma, which is a constant, over 2 epsilon naught, which is a constant. That means what I have here is the electric field. If I'm looking at, let's say, some distance r from that, a surface, is some value and never changes no matter how far away you are from the surface. That's interesting, right? It's interesting, result, because this equation does not depend on, distance. Now let's look at in terms of, let's say, some kind of metal sphere, because metal sphere is basically a conducting sphere, right? So conducting sphere, let's say, which means if you have a conductor, some distance, with the size r. And one thing about conductors is that when you have a conductor, all the charges then accumulate at the surface. They're always pushed to the surface. So then if you want to find what is the electric field at some distance r that is less than the radius, an electric field at some distance r that is greater than the radius, then the best way to do for us to find the electric field expression using the Gauss's law. Let's look at this one first. Electric field when r is less than the radius. That means I want to find electric field at some point P over here. Well, what I do here is I draw my Gaussian surface concentric sphere such that that point P is basically the same size as my sphere, Gaussian sphere, radius r. Then I want to say, all right, so I'm going to then evaluate or find the flux for that imaginary surface, which is closed integral of E dot dA. dA is for my Gaussian surface. Well, one thing I know that this is equals to Q in over epsilon naught. But I can see that in my Gaussian surface, there are no charges, no extra charges, right? Excess of charges. All the charges, right, is, let's say, at the surface. That means what I get here, Q in equals 0. So the right side of the equation equals 0. The right side equation equals 0 means that electric field equals 0 anywhere inside for r less than the radius. This is true for the metal or or conducting sphere. How about for this configuration? Well, for that one, let's say I'm finding point P over here, electric field at point P. So what I do here is I draw a surface such this, that it has a distance r, basically that exactly same as my point of interest. And I want to find what is then electric field there. Again, I apply Gauss's law. So I draw that imaginary sphere and I say, right, so I'm going to find the flux E dot dA for that surface. But because if it's a positive sphere, then electric field is going to be, moving like this, right? Radially away. And then since my surface is a concentric surface, it has same distance with respect to the sphere, electric field is constant and uniform. So E, just dA, which means the left side of my equation is then E times A. Then what is the right side of my equation? Well, it's Q enclosed or inside over epsilon naught. What is the Q enclosed? Well, total charge Q over then epsilon naught. Then what is electric field? What is Q over epsilon naught times area? Then what is the area of the sphere? Well, it's 4 pi r square then epsilon naught. So if I rearrange, it becomes 1 over 4 pi epsilon naught Q over r square. And if remember, 1 over 4 pi epsilon naught is just K. So K Q over r square. That means some distance r that is larger than the radius, it basically acts like almost a point charge, kq over r squared. All right, so this is for the conducting or metal sphere. Then let's go back and look at non-conducting or insulating sphere, because there's a little bit of difference. So we want to calculate the magnitude of electric field at the point outside of the sphere for this non-conducting insulating sphere, which is the easy one, right? So let's say I wanted to at some point P right here. So my surface, my sphere has a radius A, and my Gaussian sphere, concentric sphere, then will have a radius R. So then E, where R is greater than A. So what I do here is then I evaluate the flux for my Gaussian surface, closed integral of E dot dA. Again, because it has a charge Q, and it has a positive charge Q, then I can assume that electric field is basically going like this. At the point of interest, that means everywhere along this Gaussian sphere, it's constant. So I can say just E integral of dA, which is just E times A. And then that means this flux, E times A, is equals to Q in over epsilon naught. So what is Q inside my Gaussian sphere? Well, it's total Q over epsilon naught. Then again, E is equals to Q over A epsilon naught, or Q over 4 pi r square epsilon naught, or 1 over 4 pi r epsilon naught, Q over r square. And where this is basically nothing but K. So K, Q over r square. That means this is my electric field outside of that sphere. Okay. Now, then part B, it says find the magnitude of electric field at point inside the sphere. That means some point P right here. Then I do that. Now, what is the difference between an insulating or non-conducting sphere compared to the metal sphere where there was no electric field inside? Well, the difference here is that if there is a charge, then this charge is not accumulated at the surface, but distributed uniformly everywhere inside the sphere, something like this. Okay. That means this charge Q distributed everywhere inside uniformly like this. So then you can see, right, whenever I choose this imaginary Gaussian surface within the sphere, I have charges inside. That means what I have here is this. When I'm looking at the flux, which is then integral of E dot dA. So this is basically for the sphere that has a radius R less than A. So then, but still, electric field is constant for that surface. So it becomes E closed integral of dA. So just E times A. That means electric field, times area A, that's the left side of the equation, where's electric flux. Then this is then equals to Q in over epsilon naught. Now the question is that, what is Q in? Is this equals to total charge Q? Well, it's not. Because total charge Q is the total charge for the entire sphere. But you can see, right now I'm just considering this much of that total sphere, and I'm considering like how much charge I have over here, right, in this Gaussian surface. That means how much charge I have in this region, which obviously doesn't include all the charges, fraction of it, right, parts of it. That means we have to find a way to represent how much charge I have inside. And to do that, we use this rho, which is the volume charge density. Remember, this is total charge over total volume, but it also equals to the cube. Let me say that, for example, let's say that the charges that I have, I'm going to present as Q prime. So Q prime are the charges inside my Gaussian sphere. Okay. Then I can say that it's Q prime divided by how much volume my Gaussian sphere has, which is then V prime, the volume of that Gaussian sphere. That means also equals to that ratio. That means these ratios also equal to one another, which then allows me to write Q prime as V prime over V times total charge Q. Now, what is then Q prime? Well, equals to V prime. Well, V prime is the volume of my Gaussian sphere. It is 4/3 pi r cubed. Then what is volume V? Well, it's the volume of the entire sphere, which is 4/3 pi a cubed. That means I write this as 4/3 pi r cubed, then over 4/3 pi a cubed times q. So from here you can see, right, 4/3 pi cancels out, and my q prime is equals to r over a, the quantity cubed, times q. That means this is then the expression for q prime, either presented as a ratio of r over a cubed times the total charge q. Because I can come back here and I can say, all right, so this is then r, or I can write it like this, right? So I can say r cubed times total charge q over then epsilon naught a cubed, like that. Then I can say, then what is this area A? Well, then area A is 4 pi r square, right? And then this is equal to then r cubed q over epsilon naught a cubed. And then here I can cancel this with that. And then, over there cubed. So I end up with this then electric field is equals to q times r, then over the 4 pi epsilon naught, then a cubed. Okay. And that's the expression for the electric field anywhere inside of the sphere as long as r is less than a. Okay. Which means that if you look at the electric field as a function of r, it is linearly proportional to r. That means it increases from, it's zero at the center. So think like this: if r is zero, then electric field is zero, and then it increases linearly with respect to distance. So until you reach the radius a, and then after that it dropped as 1 over, as we know, right outside of the sphere, it drops as 1 over r square. And that's basically the graph for that. So this is the graph for the insulating non-conducting sphere, where for the metal sphere, right, conducting, it will be 0 everywhere inside. Then at the radius a, it then goes to the maximum and then drops as 1 over r square. Those are the two differences. All right. So the last thing we have is then in terms of when there is no net motion of charge within the conductor, as we basically mentioned, right? The conductor is said to be in electrostatic equilibrium. So every charge in the conductor is a particle in equilibrium. They experience 0 net force. Okay. So that means whenever you have a conductor, right, you can assume that inside the conductor, there is no electric field. And as soon as there's an electric field, right, as soon as there's some kind of charged particle inside your, I don't know, let's say sphere, they're right away being pushed to the surface, and then you have, again, electrostatic. So the properties of electrostatic equilibrium: the electric field is 0 everywhere inside the conductor. If an isolated conductor carries a charge, the charge resides entirely on its surface. The electric field just outside the charged conductor is perpendicular to the surface and has a magnitude of sigma over epsilon naught. On an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest. That means, for example, you have something like this, then see the radius is kind of like smallest. That means the electric field over there will be the strongest compared to here. Okay, so one more example here. And this one here is an electric field everywhere on the surface of a thin spherical shell of radius 0.75 meter is of magnitude 890 newtons per coulomb and points radially toward the center of the sphere. What is the net charge within the sphere's surface? And what is the distribution of the charge inside the spherical shell? All right, so let's say then what we're given here is there's a spherical shell of radius 0.75. That means, basically something like this, right there, right? So here's then the radius, 0.75, and there's a magnitude of 880 Newton per coulomb, basically electric field everywhere on the surface, 890, and points radially toward the center. That means electric field will be pointing, let's say, toward the surface, toward the center. Something like that. All right. Then magnitude then 890 Newton per Coulomb. It says, what is the net charge within the sphere's surface? All right. So then in order for us to do that, what we do here is we just choose some point P here, and then we surround it with some Gaussian surface. Well, let's say like this, right? And we want to say, all right, so let's find the electric flux, so electric field. An electric field is equals to, then this is basically K, oh, sorry, well, using the flux, right? Integral of E dot dA equals to, so it's going to be, uniform, right? So then EA, and we know that it's basically KQ over, and this is equals to, sorry, Q in over epsilon naught, okay? That means what I can say that electric field is equals to Q in is just basically some Q, right? So Q A epsilon naught, so becomes Q over 4 pi R square epsilon naught. And then if the R here is equals to then the radius, so this becomes, Q over 4 pi radius square times epsilon naught. Now, what we have here is that our goal is to find this Q, because we have the electric field, we have the radius, so rearrange and say, okay, so then Q is equals to E times 4 pi R square, then epsilon naught, then, well, that's about it. So then we can calculate in terms of what let's say the Q is. So if I calculate, then 890 times 4 pi 0.75 meters square, then times 8.89 times 10 to the negative um, 12. That's for the constant, right? And then we can calculate this Q to be 5.57 times 10 to the negative 8 Coulomb, because it's pointing inward, so it's a negative charge. Okay, then what is the distribution of charge inside the spherical shell? So then what we have is that the negative charge is a spherically symmetric charge distribution concentric with the spherical shell. Okay, so again, using this, we can find what type of net charge we have and what type of distribution we have. All right, so this concludes this chapter.